Hi class. In this last part of Chapter 16 we want to talk about masses of stars, the minimum and the maximum mass. So we've seen so far that we've got a big range of masses that stars can have. And we've talked a little bit about how the stars are born, how they're created, but is there a minimum amount of mass that a gas cloud must have to actually become a star in the first place? And is there a maximum? Could there be, big stars as big as you could possibly imagine? Hundreds and hundreds of times the mass of the sun. Is there a maximum mass? So we'll talk about those things. So what is the smallest mass? First, we'll talk about what is the smallest mass that a newborn star can have. And remember, by star, we're really talking about something that can burn helium or hydrogen into helium in the core, something that can do nuclear fusion in the core, that can get hot enough in the core to burn hydrogen into helium. So remember, those two hydrogen nuclei, two protons really, have to come together and stick. The strong nuclear force has to be able to take over, and for that to happen, the two particles, the two protons, have to get close enough together. But there is this Coulomb force, there's the electromagnetic force that's making them repel from each other. So they have to come together very fast. The faster they collide with each other, the higher the speed they have, the closer they can get. And the closer then, if they get close enough, then that strong nuclear force can actually take over and can actually make them stick together and literally turn one of the protons into a neutron. And we have that deuterium atom that we talked about before. So this requires high temperature, about 10 million Kelvin for this to happen. Remember, temperature means it's kind of a measure of how fast things are moving around. So the higher the temperature, the faster things are moving. And so the cloud has to contract enough so that the temperature reaches 10 million Kelvin before nuclear fusion can occur. So we know that as a cloud is contracting, gravitational potential energy is getting converted into thermal energy. But there are molecules and other things in the gas that can absorb that thermal energy and re-radiate it as light. And so the object that's contracting is losing energy as it contracts. It's re-radiating some of this energy. So this thermal pressure isn't going to be able to stop the contraction because the star is constantly losing thermal energy. If all we had is thermal pressure, then gravity could keep squeezing and squeezing and squeezing, and the thermal pressure would never be able to stop gravity. Gravity could just keep squeezing and squeezing, and thermal pressure would rise and rise, but so would the gravitational pressure. They would both be getting bigger and bigger and bigger, and the temperature would increase eventually to 10 million Kelvin, no matter what size mass you had, no matter how much mass you had. But what we find is that we find objects out there that are much less massive than our sun, for example, and they're not emitting what you would expect from something that has nuclear fusion going on inside the core. Look at Jupiter, for example. It's a big planet. It's certainly not doing nuclear fusion inside the core. And there are other objects out there that we can find that are also not doing nuclear fusion inside of them, but yet we can see them. They're glowing in some wavelength of light, and we'll talk about those things. But if there is some minimum mass, what that means is that below that mass, if something doesn't have enough mass, there is some kind of a pressure that is opposing gravity, so that gravity can't squeeze it any further. So gravity can't gravity can't make the temperature inside get high enough, above 10 million Kelvin, for nuclear fusion to begin. So what is this other pressure that's opposing gravity? It can't be thermal pressure, because again, the star is losing thermal energy anyway, the object that's forming, I should say, not necessarily a star yet, and as it loses thermal energy, gravity can continue to squeeze it, and eventually, both gravity pressure and thermal pressure will keep increasing with a normal gas. This will just keep happening, and a normal gas will be able to be compressed to any degree, any point, any size, so that the temperature gets high enough. But we see that that's not happening. So there's something else. There's some other kind of pressure that's stopping gravity from squeezing a star or an object enough for it to become a star. So what is this other pressure? It's something called degeneracy pressure, and it's a little bit weird because it's a quantum mechanical thing. We can't explain it by thinking about just particles bouncing around off of each other. It turns out there's something called, in quantum mechanics, there's something called the Pauli exclusion principle. And what it means is that in this case, for stars, we're looking more at the electrons really than anything else. But what it means is that electrons as you squeeze them closer and closer together, you try to make them occupy the same space. This Pauli exclusion principle says that they cannot occupy the same sort of location with the same energy at the same time. And so you just can't keep squeezing and squeezing and squeezing. And this degeneracy pressure is something that does not depend on temperature. So if you imagined you could have this ball of gas and you're squeezing it, and eventually this pressure is sort of there. It's kind of pushing against gravity, trying to prevent gravity from contracting even further. If the object were then to start cooling off eventually, you would think that if this was thermal pressure, if the temperature was going down, that thermal pressure would also go down. But that doesn't happen with degeneracy pressure. With degeneracy pressure, that pressure is still there, regardless of the temperature. Even if the object starts cooling off, that pressure is still there, and it's still opposing gravity. Even if it cools off, gravity can't squeeze it any further once this degeneracy pressure is an important factor. So kind of an analogy is with people in chairs in a room. On the left-hand side we know no two people can occupy the same chair. Let's just assume that that's a law of physics. No two people can occupy the same chair. So these people are playing musical chairs, and there's a lot of chairs available. So there's some music playing, and they're going to walk around and try to hopefully sit in a chair. But, they don't have to move very fast. They can just kind of mosey around, and they don't have to worry too much about finding a chair because there are a lot of chairs available. Once the music stops, they just plop down in a chair and everything's fine. And so this is like, non-degeneracy pressure. They're not really worried about finding a location in a sense, an energy in a sense. Think about the chairs as being particular energy states that the people, the electrons, can have. But if you squeeze them together really tight, that's like removing some of these chairs, and you have this situation where there's almost like there's more chairs than there are people. Or there's more people than there are chairs. There are more electrons than there are energy states available. So we've removed some of these locations where the people can be, where the electrons can be. And so as the music is playing, people have to move around pretty fast. They want to get around really quick. They want to be by one of those chairs. So they're kind of fighting it with each other in a sense. There's more pressure there in a sense. And when the music stops, they're rushing around to find a chair. Right? So it's kind of analogous. It's of course not the same because it's very hard to do analogies between quantum mechanics and classical mechanics and have those analogies explain everything. It just doesn't quite work that way. But it's sort of like this, that you've got these electrons, gravity's trying to squeeze them together, and they're all trying to rush around to find kind of a place to settle down in. And the more they get squeezed, kind of the faster they have to rush around to find sort of a place to settle down in. And that results in an increase in pressure, but it's not a thermal pressure, it's this thing called degeneracy pressure. When we put all the electrons in sort of these chairs in these states, we say that the gas is degenerate. There's this electron degeneracy pressure, and gravity just simply can't squeeze it any further. Up to a point. We'll talk about the possibility of actually being able to overcome this electron degeneracy pressure in the next chapter. So that's the idea. Again, thermal pressure is like what you find in a balloon. As you heat up a balloon, as you heat up the gas in a balloon, the thermal pressure increases, the volume then increases because the pressure increases inside. So thermal pressure is dependent on temperature. You can increase temperature, thermal pressure goes up. You decrease temperature, thermal pressure goes down, and so on. You heat up the gas, the balloon gets bigger because of the increased pressure. You cool the gas, the balloon gets smaller because of the decrease in pressure. With degeneracy pressure, it's different. The temperature doesn't matter. So in other words, if you have a degenerate gas of electrons, and all the electrons are occupying their states, and there are no other available states for an electron to go in, then you can't decrease that pressure any further, even if you decrease the temperature. So even if you decrease the temperature, those electrons are still not going to be able to get closer together. They're just going to be pushing against each other. And again, this is not because they're all negatively charged, because there's a repulsion between them. It's a different kind of thing. It's a purely quantum mechanical phenomena it's again hard to explain by just drawing analogies between quantum mechanics and classical mechanics. So you just have to kind of accept this as a strange idea maybe, but it comes from quantum mechanics. and it isn't like thermal pressure in that it does not depend on temperature. So a brown dwarf is something that we refer to as an object that is kind of almost a star. It hasn't quite gotten there yet. And what we can see, what we can find both observationally and as well as theoretically doing calculations, is we find that anything that has a mass that's less than 0.08 times the mass of the sun is something that will not get its core temperature high enough to start nuclear fusion before that degeneracy pressure kicks in. So that degeneracy pressure will stop gravity from contracting the star more tighter, in a sense, smaller. If the degeneracy pressure was not there, gravity could keep squeezing and squeezing and squeezing, no matter the mass, and the object would eventually get hot enough. But there is this thing called degeneracy pressure that takes over at some point. And for objects that don't have enough mass, degeneracy pressure takes over before the temperature gets high enough. And so the object, once it reaches this point, once it reaches a certain size where degeneracy pressure is sort of preventing gravity from making it smaller, it just stays that size, and it doesn't contract any further. And the object doesn't get hot enough inside to start nuclear fusion. And so it isn't quite a star, but it's sort of like a star. It's still very hot, not really hot, but it's still pretty warm. And it gives off light, but it's not a lot of visible light. It's mostly infrared because it's not that hot. And so we refer to these things as brown dwarfs. And there's a couple different classes of brown dwarfs that we'll talk about. So the brown dwarf does emit infrared light because it is hot, and all that light, that heat, that energy that it's giving off is really left over from its contraction. Again, the conversion of gravitational potential energy into thermal energy. The luminosity then is just the amount of energy it gives off every second, which is then gradually decreasing over time because it's not producing any more energy inside. All the energy that it has to give off has already been kind of made, in a sense, by gravitational contraction, and no more gravitational contraction is happening. So if we go back to these spectral classes that we talked about before, these are the spectral classes of basic stars that we've seen, main sequence stars, O, B, F, G, K, M. And these were the O stars, remember, were the really, really hot big stars, the blue stars. And then the B, A, F, G, our sun is a G star. K and M were red dwarfs. We can now that we've discovered brown dwarfs, the first brown dwarf was discovered in 1995, so not that long ago. Now that we've discovered them, they found that there's 3 different types of brown dwarfs, and they behave a little bit differently. What you see in their spectrum is a little bit different. So there's L types, so we'll have an L in here after the M, and those are brown dwarfs that have surface temperatures between about 2200 Kelvin and about 1400 Kelvin. So they're cooler than regular, red dwarf stars. And we call them L stars. And L stars are kind of a mix. There are some L stars that are sort of producing some nuclear fusion, but not that much. And there are some L stars that are not doing any nuclear fusion. So this is a class where there's kind of a mixture of both true stars as well as brown dwarf stars. The T class is even smaller than that. And again, we're looking at the spectrum of these stars and identifying different elements. There's different absorptions that are occurring in the spectrum, and identifying the atoms and molecules and things like that are causing that absorption. And we can measure the temperature from that. So these T stars have a temperature from about 1500 to 500 Kelvin, and they're definitely not hot enough. They definitely don't get hot enough inside to produce any nuclear fusion. And the Y stars, and again, these are not really stars, these are brown dwarfs. They're not technically stars, but the Y class is also not producing nuclear fusion. These are things with surface temperatures of less than 500 Kelvin. So these are Y brown dwarfs. So the brown dwarf, a true brown dwarf, is something that is not producing nuclear fusion in its core, and it's something that has a mass less than 0.08 times the mass of the sun. And it's important to realize that, you might think, well, is Jupiter pretty close to that? Well, no, 0.08 times the mass of the sun is about 80 times the mass of Jupiter. And so Jupiter is nowhere near being close enough to even being considered a brown dwarf. It's still considered just a planet. So it's not even close inside Jupiter to being hot enough to do nuclear fusion. So I'm going to look at a little animation here. So I've shown these before. This is the PHET simulations at the University of Colorado. And there's one in here under the physics, heat, and thermo, one called gas properties. I just want to kind of review something really quick. So this is what it looks like when you open that one up. And just to kind of remind you of the properties of regular gases really quick. So we'll pump some air in here, some gas in here, and we're pumping something. It might be, whoops, I have to play this. Okay, so it might be, let's pump the gas in there, let it bounce around a lot. So we pump some gas into this area, into this chamber, and nothing's happening. The gas is coming into sort of an equilibrium. The pressure has gotten up to some value. The temperature is some value. And what I can do is we can try to cool this down. And so gases behave in this way. When you cool them down, so I'm going to put ice underneath the container. Watch, the pressure is going down and the temperature is going down. Of course the temperature is going to go down if we cool it down, but the pressure goes down too. So with a normal gas, pressure and temperature are related to each other. So I've brought the temperature down pretty far, and therefore the pressure has gone down. The gas atoms are moving around a little bit more slowly. They're not hitting the walls of the container as fast. So what can I do to bring that pressure back up? Well, I can squeeze the gas. I can try to squeeze it. So this is like gravity trying to squeeze the gas. So gravity is going to try to squeeze the gas, and look at how the temperature goes back up and the pressure goes back up. If we bring the pressure back up to about where it was near about 1 or so. Let's just keep squeezing. Right there is pretty good. So the pressure now has gone back up, the temperature has gone back up because we've squeezed the gas. And that's like what gravity is doing. Gravity is squeezing the gas, causing the temperature and the pressure to increase. So this is the thermal pressure that's pushing against gravity to try to make gravity stop. Well, what this degeneracy pressure is very different. It's different from what a regular gas will do. And I can't demonstrate it with this simulator because it just doesn't do this. It just doesn't demonstrate this. But if I were to now cool this gas, again, put ice under the gas, if I were to now cool this gas, if this was a degenerate gas, if I were to cool it, you would see that this pressure would no longer decrease. The pressure would remain constant if this was degeneracy pressure. So if I got these gas atoms so close together that the electrons were saying, hey, wait a minute, we don't like to be at this close together, and it's not because of our negative charges that we're pushing against each other, it's simply because of this quantum mechanical thing called degeneracy pressure. If I tried to cool the gas, I could cool it, the temperature would go down, that would be fine, but the pressure would not go down. And that's different from what happens with regular gases. So, and that's because of this thing that's not regular, this thing that's purely quantum mechanical called degeneracy pressure. So that's what's preventing brown dwarfs from actually getting smaller for gravity to be able to contract them more, to be able to form an actual true star, to be able to get temperatures high enough to actually trigger nuclear fusion. So those are different spectral classes. We have evidence of brown dwarfs by looking at infrared photographs of clouds of gas and dust out there. So remember, these brown dwarfs are very cool, so they don't give off a lot of visible light. Maybe a little bit, but it's in the deep part of the red. A lot of infrared light is what they give off. And so this photograph shows a bunch of little circles, and you can see some little dots in there if you look carefully. There are some little visible dots in there, but if we look at this in the infrared, it looks like there's definitely some things. There's definitely objects there that are brighter in the infrared. So let's go back. This is one of the interactive figures that I have available in the D2L site. This is the visible photograph of that same object. I don't have those circles drawn, but let's go to the near infrared and just see what appears. So we're looking at the visible part of the spectrum. We're looking at visible light, a photograph that you might take with your camera and a telescope. But now if I look at it through the near infrared, so colors that are a little bit deeper red than the red that we can see with our eyes. So near infrared. So there you can see some things pop out, things that you didn't see before. Let's go back and forth. You can kind of see through the cloud too, and you can see stuff that you didn't see before. And now if we look at the mid-infrared, so this is even more infrared, you can see things a little bit brighter now. So these are your brown dwarfs. These are things that are very much giving off a lot of infrared light because they're at a temperature that is high enough, or low enough, I mean, so that it's not giving off a lot of visible light, but it is giving off a lot of infrared light. And then we can look at radio waves as well, and we see a lot of stuff in here, but we don't see a lot of those little dots anymore. There's not a lot of radio waves being given off by the brown dwarfs, but there's definitely a lot of infrared, near infrared and mid infrared being given off. So go back, look at that. Go from there, near infrared, that's mid infrared, near infrared, and you can see some objects appearing and disappearing. Look in this region right here. You don't see anything in the near infrared. Click the mid infrared, and now you see some stuff. those are your brown dwarfs, giving off a lot of infrared light. So if we go back then, brown dwarfs, again, are these objects that have the minimum mass, or they're below the minimum mass to form a star. And again, the reason for that is because of this degeneracy pressure that occurs, that is sort of triggered once electrons are getting pushed closer and closer together. They just do not want to get closer together. And it's, again, a purely quantum mechanical thing. What about the biggest mass? What is the biggest mass that a star can have? So what happens with bigger mass is that the more mass you have, the hotter the core can get. And eventually, when it becomes, as it becomes a star and as it starts producing nuclear fusion, it's producing more and more light energy. More and more photons are coming out. And so photons themselves actually can push on material. So not only is there a thermal pressure pushing outward against gravity, but there's also this radiation pressure, the pressure of light itself pushing outward against gravity. And so the more massive a star is, the brighter it is, the more energy it's producing, and the more photons that are coming out of it, and those photons exert pressure on the matter that the star is made of. And so the brighter the star, the more the nuclear fusion is happening, the higher this radiation pressure is. Eventually, this radiation pressure can actually push material outward, out of this object, away from this object. And so if we look at models of stars, it shows that this radiation pressure can actually limit how big a star can be. Because the bigger the star is, the brighter it is, the greater the radiation pressure it has, and the bigger that pressure is to push material away from it rather than allow material to accumulate. And so so a while ago it was thought that the biggest mass of a star could be around 150 solar masses. But there has been some new observations that indicate that there could be some stars that are even bigger than that. 150 to 200 solar masses, maybe 300, there could be some special cases, but there definitely seems to be an upper limit on a star's mass, because the higher the mass, the greater this radiation pressure, and it just basically doesn't allow more material to settle down on the star. This radiation pressure just like blows everything away from it. So it's almost like the star is blowing itself apart, but it's not like a big explosion. It's not like a supernova explosion. It's just like a really intense solar wind that is, but it's not particles, it's photons that are pushing particles away, not allowing them to accumulate on this big massive star, keeping it from getting any more massive than somewhere around 150 to 200 or so solar masses. So when we look at that on the main sequence, our very lowest, very lowest mass main sequence stars would be around 0.08 times the mass of the Sun. Anything smaller than that can't start nuclear fusion. It can be able to start it, but it can't maintain it for very long at all. It can't sustain nuclear fusion, so it can't be a true star. On the other hand, anything bigger than about 150 or so, maybe there's a few exceptions to this, anything bigger than that is just so intense, so bright, so much radiation pressure that it kind of blows itself apart, and it just doesn't last very long. So when we go and we look at clusters of stars to measure what kind of stars the clusters are made of, what we find is that the majority of stars that are formed are small stars, low mass stars. And so in this cluster that has a total of, 261 stars, out of the 261 stars, about 200 of them are going to be low mass stars, between 0.08 and a half the mass of the Sun. And about 50 stars, roughly, will be between 1/2 and about 2 times the mass of the Sun. So these are low mass stars, these are kind of like medium mass stars, and these are high mass stars. And 10 stars are in the 2 to 10 times the mass of the Sun, and only 1 star is between 10 and 150 times the mass of the Sun. So this is our observations. This is what we see. We see that clouds of gas and dust primarily form low mass stars. It's a lot easier to form a low mass star. It's a lot harder to form a high mass star. And what's interesting then, of course, as we've talked about, is that these high mass stars don't last very long. They live a very short life and they're gone very quickly. These very low mass stars last forever. In fact, all these stars that have ever been formed, these really low mass stars, none of them have died yet. They live for billions of years. And the universe, as we know, is only about 14 billion years old. And these low mass stars can live for 100 billion years, possibly, the very low mass stars. So this is what we see. The majority of stars are low mass stars. Our Sun is kind of an average, sort of medium mass star. And then there are some big mass stars, but not very many. And you might think, well, it seems like there's a lot. When you look out in the sky and you look at the bright stars we see, Betelgeuse, Sirius, and so on, it seems like there's a lot of those bright stars, those big bright stars. Well, it seems that way because they're easy to see. They're very big and bright, they're easy to see. When we look at other wavelengths of light, and we look at these dimmer stars, these lower mass stars, we find that there are a lot more of them than there are of these big bright stars. So these low mass stars are just more difficult to see. It doesn't mean that they're not there, it just means we have to look a little more carefully. So what have we learned? The degeneracy pressure stops contraction of objects less than 0.08 times the mass of the sun. And so anything lower than that is going to be a brown dwarf, or possibly a planet, depending on how small it is. So there's always this fuzzy line between when you define a star versus a brown dwarf versus a planet. So we haven't talked about at what point do you say that something's a planet, but clearly it has to be orbiting a star to be a planet. And then the greatest mass star, we found that anything bigger than about 150 times the mass of the sun would be so bright that the radiation pressure would just blow the thing apart. It wouldn't, again, be like a supernova explosion, but it would be kind of like a really intense wind that blows more material off the star, so it just can't get more massive. That's the end of Chapter 16. In the next chapter, we're going to talk more about these specific sort of categories of mass. We'll look more carefully at low mass stars and what's happening inside of them. We'll look more carefully at kind of medium mass stars and what are the differences between these medium and low mass stars and the really massive stars. What are the differences internally between these different stars? And why do the big massive stars die so quickly? Why do the low mass stars live so long?